Hello, my name is Rui Cardoso. I'm Senior Lecturer at Brunel University London, UK, and I'm going to deliver a short course on numerical methods for structural analysis. We will start with the weighted residuals, and then the final goal is to get into the finite element method, which is the most common used method in structural analysis. Before I start, I would like to give this information. So I recently published this book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. This book includes, so it is a 700 pages book. It includes many introductory chapters, but the chapters we are going to focus in this short course is going to be numerical methods, basically this chapter 10 and also chapter 11. So like I said, we will start with the weighted residuals method. Okay, we'll talk about Galerkin's method, collocation method, and then we will move to weak formulations, which is very important to derive the finite element matrices for elasticity. And then we will, in this section 10.4, we will derive some important formulations for some specific elements, for 1D elements, 2D and 3D elements. In chapter 11, we'll focus more on plate and shell elements. Okay? So in this short course, so these are some figures I took from my book. So you will be able to model this kind of structural components. For example, an hinge. Okay. So you have MATLAB scripts to get the finite element matrices for the 3D elements, brick elements. That is included in the book. So you can predict the equivalent von Mises stress. So the pin here is modeled as a rigid body, but then the other two parts of the hinge, they are deformable bodies, and you can see the distribution of the von Mises stress. You can also see the distribution of displacements or wherever else you want to see. Also in the book, in the chapter for plates and shells, you will you have basically the MATLAB routines to build the shell elements, and if you want to implement that in your MATLAB code, you can get results similar with these ones. For example, this one with a cylindrical shell with a concentrated force, so you get the deforming configuration, something like this. So this is something you can predict with the MATLAB scripts in the book. So another type of things you can do from the book is a buckling analysis, getting the buckling modes for a plate element, in this case with some symmetric boundary conditions. You can get different buckling modes and predict the structural behavior of these structural elements under compressive or in-plane shear loading. Okay. So what we are going to learn in this short course is basically the weighted residuals and finite element method. So with the weighted residuals is the foundation to get the finite elements that allow to do this kind of problems, analysis of this kind of problems. So I hope this short course is valuable to you. So yeah, that's it. Hi everybody. Let's continue this short course on numerical methods. So today I like I promised in the previous session, I will introduce the weak formulation for the theory of elasticity. From what we are going to do today, you will be able to build the different finite element formulations, or to derive the finite element stiffness metrics for each element, different types of elements. and the force vector, and then from that you will be able then, by just solving a linear system of equations, to obtain the unknowns, which are the degrees of freedom at the nodes of your elements. So the derivation of the weak formulation for the theory of elasticity is quite critical to do this. So the starting point is going to be, so we are going to base, like in the previous sessions, everything on the weighted residuals. So we learned already how to build a residual, a weighted residual, and we learned how to build an approximation function, and we did learn as well the weak formulation, which was basically integration by parts. We did learn all of that, right? So now our residual is going to be the equilibrium equations for elasticity, okay? So you know the equilibrium equations, I can write. So it's the derivative of the stresses you can write like this, plus volume force, sorry about this, equal to 0, right? So this is the equilibrium equations that I think you learn. So of course this you learn this in the typical solid mechanics courses. This is elasticity, right? So basically, okay, if you, just very quickly some details. So the first equilibrium equation is, for example, the derivative of sigma xx in order to x plus the derivative of tau xy in order to y plus the derivative of tau xz in order to coordinate z plus fx equal to 0, right? So the second equilibrium equation is the derivative of tau yx in order to x plus the derivative of sigma yy in order to y plus the derivative of tau yz over to z plus fy equal to 0, and the third equilibrium equation is going to be the tau z x in order to x plus derivative of tau z y in order to y plus the derivative of sigma z in order to z plus fz equal to 0, right? So basically all these three equations, they are represented in this generic way here. So these are the equilibrium equations that you did learn in solid body mechanics or any other mechanics of structure, and introduction to mechanics of structures, or this kind of courses, right? Okay, so what we are going to do now is basically what we are going to do is now to build the residual. Okay, so let me just copy this to a new page. So this is our equilibrium equation. Maybe I can zoom a little bit. And what we are going to do is, remember when we built the weighted residuals in the previous sessions, we said, okay, we have our differential equation. We need to have on the right hand side 0, and then on the left hand side, what it is left on the left hand side, the that is going to be my residual after I replace my the function the variable I'm looking for to solving the differential equation after I replaced it by my approximated variable or approximated function, right? In this case, my goal is to get my stress field. So I'm going basically to approximate my stress field with a sigma hat, okay? Alright, so basically if I replace sigma here in this differential equation by sigma hat, instead of 0, I will get something approximately equal to 0, which I will need to minimize, and then that's when I get my weighted residual. So we did learn how to do that in the previous sessions. I'm not going to spend too much time here. So basically, my residual is going to be, if you want, my residual is going to be equal to the derivative of my approximated stress field plus Fi, okay? So far, nothing special. I didn't do anything special, I just got my differential equation, which is the equilibrium equations for elasticity, and I'm getting the residual by replacing the exact stress field, sigma, with an approximated stress field, sigma hat. The next step is to multiply this residual by a weighting function. That's what I'm going to do. So my residual I will multiply this residual by a weighting function, and then I will integrate this residual over the domain, which I call omega. So the domain of my problem is going to be omega, okay? So this is my weighted residual, and I'm going to say that this needs to be equal to 0, okay, because again the idea is to get this residual as close to 0 as possible, right? And for every single point of our domain. So again, this was, if you are not following what I'm saying, I recommend you to see the previous sessions that you have in YouTube. We talk in detail about this weighted residual, okay? There is one thing that I'm skipping here is, okay, we are approximating, we are getting the weighted residual for the domain of my problem, but we know in elasticity that we also have boundary conditions. For example, I might have a stress vector at some boundary. So the stress vector, maybe I can, yeah. So stress vector is given by the stress tensor, right? Where you have the stress components times the normal vector, normal to the shear plane, right? So I might have some of these kind of boundary conditions. So one way of incorporating these into our weighted residual is by sending the right hand side to the left hand side. Okay, and then this is what is going to be the residual at the boundary. And then what I can do is that I can also minimize this residual at the boundary by adding here a weighted residual now with the domain on the boundary, and that's this weighted residual the residual is going to be this one, right? This is going to be the residual. And then I will have to multiply this residual by a weighting function, which I will say is a weighting function. I'm going to do this in the boundary, define it in the boundary. And then if I impose all of this equal to 0, I basically will be able to obtain my approximated stress field that fulfills the domain of my problem and also the boundary of my problem, right? So this is what is done traditionally. So if you see in my book, this is detailed explained. But for the purpose of this short course, what I'm going to do, and also because in finite elements we apply the boundary conditions in a very different way. So what I'm going to do is I'm going to skip this approximation of the boundary conditions from the weighted residual and make things a bit more simple. Okay? So we are going basically to work only on minimizing the residual in the domain of our problem. Okay? So let me copy this in this new slide. So we will continue the derivation from here. Right. So next step, what I'm going to do is just to separate this integral in two. So we will have integral in the domain of, so this is the first term. And then we have this other term here. Nothing special, as you can see. I didn't do nothing special so far. Now, the next step, yes, is the more important one. I'm going to apply the green theorem, which in one dimension is equivalent to integrate by parts, which is in the previous session in YouTube. We started with formulations using the integration by parts. So in this case, I will use the green theorem, which is equivalent to integrating by parts, but when you are dealing with a 3D, like we are here for the stress field, right? We have stresses in the X, Y, and Z direction, direct stresses and shear stresses. So you need to use the green theorem, but as you will see, is very equivalent to integrating by parts. So I will keep this second integral unchanged, right? And I will apply the green theorem only to this term here, okay? So if I do that, I get minus integral in the domain, and I will have derivative now of my weighting function in order to xj, which will multiply my approximated stress field. And I will have, of course, then integral in the boundary of my approximated stress field times a normal to the shear plane. So this is because of the green theorem. And this will multiply by my weighting function and all of this integral is defined in the boundary. This is the result of integrating this integral by parts, right? We have an integral in the domain and an integral in the boundaries of the problem, right? And I only need now to add the remaining integral, so plus the remaining integral that is there in the domain, the volume force times the weighting function, equal to 0, okay? We can organize this in a more convenient way, so I'm going to copy this result of using the green theorem to a new page. Okay. Right. So this, the product of the stress tensor with the normal to the shear plane, we know this is the stress vector. So I can basically then write something like this. So this first one, I will keep it. I will multiply everything by -1 as well. So you will have, I can maybe just switch sigma with the derivative of the weighting function for convenience, nothing special. And then I will send this and these integrals to the right hand side, so they will become negative, but because I'm multiplying everything by -1, so they become positive. So I will have integral in the domain of the volume force times the weighting function, plus the integral in the boundary. So this is stress vector. So the stress vector is this, Ti, which multiplies by a weighting function. Right? This is a very important result, which, again, doing a very, very quick summary, why we arrive at this. Basically, our starting point was the equilibrium equations from elasticity, which is a set of differential equations. Second step was to get an approximation function for sigma, which we didn't define yet, but I just replaced my exact sigma with sigma hat in the differential equation, and by doing that I got the residual. The third step was multiply the residual by a weighting function and integrate it over the domain of our problem and make all of that equal to 0. Then the fourth step was just using the green theorem to obtain this final equation that you see here on screen, okay? And now the most interesting and important stuff for finite element analysis is coming now, and it's quite important what I'm going to do from this point, okay? All right, very good. So let's continue copying this again to a new page. Right? Now, what I'm going to do is to build my approximation function not for sigma hat, but for the displacement field. I'm going to build an approximation to my displacement field. So when I do this below my variables, it means it is a vector or a tensor, okay? So I'm not going to work anymore with components. In fact, I think in the previous one I forgot to include here the components I, j of my stress tensor. So I'm going to work now with tensor notation or vector notation. So I'm going to say my displacement field is going to be approximated by, similarly like we did in the previous two sessions that you have in YouTube, when we introduced the weighted residuals, when we built an approximation function. I'm going to do a summation of shape functions. I will call n times times an unknown displacement field. You remember when we built approximation function phi previously in the previous sessions for the weighted residuals, we said this approximation function. I think we did that for a beam, so we built the approximated deflection as a summation of the shape functions, we call it phi, remember, times unknown coefficients. So if you compare these two, I'm doing exactly the same thing. The only difference now is that my unknown coefficients, ak, they are going to be also unknown, but now displacements. And in the finite element terminology, these displacements are located at nodes. We call them degrees of freedom, okay? So they are our unknowns when we built our approximation function. And the shape functions that we defined before in previous session, I'm going to call them now nk. So they are still shape functions, and they will depend on the type of finite elements you are going to use. For example, if you look at 2D finite elements, if you are going to use triangular elements, you will have a well-defined set of shape functions. If you are using a quadrilateral element, you will have also a different set of shape functions, very well defined for that type of element. So what I'm trying to say is that, and like I said in previous sessions, the shape functions, they are defined a priori, right? So we know what are the shape functions. For the finite element analysis, they depend on the type of elements you are using. Okay? So this is the approximation function we are going to build. Now, I cannot just insert this approximation function directly on these integrals I have derived from the Green theorem. So, but it's quite easy to arrive. For example, if you have in mind that the stress, so this or this, when I write this or this, is the same thing I'm referring to, right? So, like I said, I'm just using the tensor notation now for convenience. So the stress tensor, is obtained by the Hooke's law, right? You have the elastic matrix with the elastic constants, such as the Young modulus and Poisson ratio. And then if you multiply that by your strain tensor, this is basically this what you have here. I can write here, this is Hooke's law, right? Okay? And the good thing about this is that, well, the good thing is not the good thing, but the deformation tensor is going to be obtained by the derivatives of the displacement field in order to the x, y, z coordinates, right? This is, well, if you look, for example, I don't want to spend too much time on this, but anyway, if you look on a specimen that when you do a tensile test, right, you will have your L after stretching the specimen compared with your initial L0, for example. Then you can define delta U as L minus L0. Okay, so, and your strain you say is L minus L0 over L0. This is the engineering strain. Basically, you are saying this is equal to delta U, right, over L0. And you can see some, if this delta U is very small, infinitesimal in the limit, when this tends to 0, you get the derivative of the displacement field, right? So this is basic stuff from elasticity. So as you can see, so let me just delete this. As you can see, we will basically inject our approximation field for the displacement. We will inject this in these integrals by injecting it. So let me see here, doing the derivatives of this displacement field. Then you get the strain. The strain then is injected in the Hooke's law. Then you get the stress field. Once you get stress field, then you can replace it in your equation with these integrals. Okay? That's what we are going to do. We can write this approximate displacement field in the matrix notation, which is more convenient for finite element analysis, because don't forget, this finite element analysis, all of this we are doing here, it needs to be implemented in a computer, it needs to be programmed or coded. So it's much easier to get the displacement field in the x direction, y direction, and z direction by multiplying a matrix with shape functions, something like this. Okay, if you hold on a second, you will understand this. So this is shape function number 1. Then you have shape function number 2, 3. So depending on the number of nodes of each element in finite element analysis. So let's say the total number of nodes per element is m. So you will have then here shape function m. Okay. And then this will multiply the vector. So this is going to be the displacement in the x direction for node number 1. So degree of freedom u1, displacement in the y direction for node number 1, displacement in z direction for node number 1, and then it goes all the way, and then you get displacement in the x direction for node M, displacement in the y direction for node M, displacement in the z direction for node M. So if you do the multiplication of this matrix with this vector, basically you are doing this summation that you have here that allows you to obtain your approximated displacement field. Okay? This matrix is also known as the matrix of the shape functions. I'm going to, instead of writing this matrix every time, we are going to use this n with this underscore there because it is a matrix. And this matrix depends again on the finite element that you are using in your analysis. Okay, so for example, if you are using a finite element with quadrilateral elements, a quadrilateral with 4 nodes, for example, plane stress and plane strain, you will have a matrix of shape functions. If you are using, for example, same quadrilateral with 4 nodes, but for plate analysis, you will have a different matrix of shape functions. If you are using for shell analysis, you will have a different matrix of shape functions. If you are using a brick element with 8 nodes, or an hexagonal element with 8 nodes, you will have a different element, a different matrix with shape functions. So this matrix of shape functions depends a lot on the elements you are using. Now, this vector here, the vector of unknowns, or the vector with the degrees of freedom, after replacing all of these in those integrals and in the weighted residuals, in the integrals there, at the end we will arrive at the system of equations where we have the stiffness matrix, after assembling the contribution of all finite elements. Don't worry, we are going to see how to do that, times this vector of degrees of freedom going to be equal to force vector. So this is basically a system, a linear system of equations where you will solve for this vector of degrees of freedom at the nodes. And how do you solve the system of equations? By inverting the stiffness matrix and multiplying by the force vector. So what we are going to see now is, so this is quite easy to do in a computer, solving a linear system of equations is quite easy to do. So what we are going to focus now is how can we obtain the stiffness matrix, K, which is quite critical, and how can we obtain the force vector, F, right? Okay. Let's continue. So, our strain tensor, approximated strain tensor, as we have seen, is the derivative of our approximated displacement field. We have seen this, right? So if I replace, so I can do like this, is maybe easier. So derivative in order to x, y, and z. Now my approximated displacement is going to be given by the matrix of the shape functions times my vector with degrees of freedom, or the vector with my unknowns. So that's what we have seen. So I didn't put here. So this is my vector with my degrees of freedom, right? So we have seen this. So this vector with the degrees of freedom, so these are unknowns, constants. So this means that my derivatives is going to be the derivatives of my shape functions in order to my coordinates, right? And now this is the first term that I'm going to introduce here that belongs to the finite element world, if you want. So these derivatives of shape functions, this is known as the B matrix, also known as the strain displacement matrix, okay? It's quite easy to see why. Look, it's very easy to memorize because on the left hand side you have the strain field, and then this strain displacement this B matrix allows you to obtain the strain field from the displacement field, right? That's why it's called strain displacement matrix. Quite easy to memorize. And basically, this B matrix is the derivatives of the shape functions, which, as you have seen in previous sessions when we built I think we did some examples for beam deflection. We built the shape functions from polynomials, right? And the derivatives of those polynomials in order to x in that case, because it was only one dimension example, it was quite easy to do, right? We had derivatives of x squared, x cubed, so quite easy to do. So in this case, the shape functions are defined depending on the elements you are using, finite elements you are using on your mesh, and the analysis you are doing. So the derivatives of shape functions in order to x are going to be very straightforward as well, so there's no problem at all. Okay? Now, I can write my approximated strain field as a product of my strain displacement matrix times my vector of unknowns or vector of degrees of freedom. And I can replace from the Looks law, I have my stress field equal to my matrix with elastic constants times the strain field. So if you want, my approximated stress field is going to be equal to my matrix with the material constants, elasticity matrix from Hooke's law. And now the strain field is going to be replaced by the strain displacement matrix times the vector with the unknowns or the vector with the degrees of freedom. And now this is quite important because this is what I need to replace here in this integral. Right? There is also another thing that I didn't tell you so far, but that I did in the previous sessions, which is related with the weighting functions. So we have the derivatives of the weighting functions here, and we have the weighting functions here and here, right? So if you remember from the previous sessions, we used the Galerkin's method. We said that the weighting, so maybe I can do it here using Galerkin's method. We say that our weight functions, they're going to be equal to our weighting functions are going to be equal to our shape functions, right? This leads to a very important characteristic. I don't know if you still remember, but you can check in the videos in YouTube that the resulting stiffness matrix, this matrix K, is going to be symmetric. This is quite good because then you can use a symmetric solver for the linear system of equations, which makes all of this much quicker in computer calculations, right? Using the finite element method. So this was one advantage. There are more advantages of Galerkin, but I recommend you to check the previous videos on YouTube, okay? So what I'm going to do now is, I'm going to copy these integrals here, these weighted residuals that we obtained here for the theory of elasticity. I'm going to put them in a new page, I think it's better. And we are now we are in conditions to replace the stress tensor and the weighting functions in this. So then we can arrive to a very important conclusion. That's what I'm going to do now. Okay, so the stress field, this one, this is the stress field we will need. So I'm just putting it here. This derivative here, that you have there, basically using Galerkin's method, is going to be the derivative of the shape functions. Okay, and we have seen that this is equal to our strain displacement matrix B. Okay, so if I replace now, if I work out this integral, here I will have integral in the domain the derivative of the weighting function is equal to the derivatives of the shape function is equal to the strain displacement matrix B. So this is my dw dx times the stress, which is given by this equation here. So we have the matrix with the elastic constants multiplies by the strain displacement matrix and multiplies by the vector u with the degrees of freedom or with the unknowns. But I'm going to send, because this is constant, they are constants, right? They are the degrees of freedom at the nodes of the element. So they are constant. I can send outside of the integral. So I'm going to close my integral here. And I will then, maybe I can put, and then I will send my vector with degrees of freedom outside of this integral. So the only thing that is missing here, or is not correct, 100% correct in this integral, is that this first strain displacement matrix needs to be transposed. Okay? And we are going to see this is going to be my stiffness matrix. All right? But I will write this down at the end. So this integral is done. The integral on the left hand side. Now the integral on the right hand side is going to be my force vector. So this is going to be my force vector F. But I will put put it here in a different way. The Galerkin method, so the weighting function is equal to the shape functions times the force vector. And the other one is in the boundary. Again, using Galerkin, weighting function is equal to the shape functions times the stress vector. You see? So look at this. We have only products of vectors and matrices. In this, the only thing that we need to do, I deleted this one here, I don't know why. The only thing we have to do now is to do the integrals, and we are not going to do the integrals today, is in the next session. I'm going to dedicate next session to numerical integration, which is quite an important thing in FEA. So when you use a finite element software package, you always hear about nodes, and you know the nodes is where you have the degrees of freedom, this U, right? These U variables here, they are at nodes. We are going to see then, not today, for different elements, how you define these degrees of freedom there, and how do you assemble them in the stiffness matrix. Not the degrees of freedom, sorry. How do you assemble the contribution for the global stiffness matrix of the stiffness of the individual finite elements? That's what I wanted to say. Sorry, I forgot what I was about to say. I'm going to do a pause until sorry. Yeah, all right. So I was talking, about having on these commercial softwares different things like nodes where you have degrees of freedom, and also integration points. It's something that you see when you use this commercial, this finite element software. Integration points. So you know why you have integration points for now, because we need to do these integrals. We need to integrate. So in the weighted residuals, we have to perform these integrals. And we need, if you are implementing this in a computer in an automatic calculation, you need to have a way of doing numerical integration. You cannot do analytical integration, right? The computer does not know how to do analytical integration. So, for example, when you have a quadrilateral element, it's quite common to have an element where you have nodes at the vertices of the quadrilateral, 4 nodes, and then you have inside the element, you have, for example, 4 integration points. And the location of these integration points in the element is very well defined. So the reason why you have these integration points is to do these integrals. And also, everything you calculate, like the strains and the stresses, they are calculated at integration points. Okay? Each integration point will have a value of the stress and strain. So you're starting now to get familiar with this finite element terminology. Now moving on, so we are almost finishing the session. I just want to get this final result we obtain in a new page and write it in a different way. Not in a different way, in a very simplified way, where we will have the stiffness matrix, the global stiffness matrix of our problem, times the vector with degrees of freedom, which are our unknowns, equal to our force vector. So this is my stiffness matrix, and this is my force vector, okay? So this stiffness matrix includes the contribution of all the elements. So when you do a mesh, you are dividing your domain, omega, into smaller subdomains, right? And then you need to do a loop into all these elements and get the contribution of all the stiffness matrix for all of these elements, and assemble that contribution in this global stiffness matrix. Okay? Same thing for the force vector, so we will see how to do that. And then at the end, you just solve the system of equations for the unknown vector with the degrees of freedom u. So you get the degrees of freedom u. So once you get the degrees of freedom u by solving the system of equations, right? By doing this, you calculate for each element, you calculate at each integration point, you calculate the strain field by using the strain displacement matrix. So this is done. Okay, I can put something for each integration point. And of course, of each element, you calculate the strain. Once you get the strain, you calculate the stress field by using Hooke's law. Right? So that's what you'll get in your FEA. So you get the displacement field first by solving a linear system of equations, and then for each element and for each integration point of each element, you calculate the strain from the displacement field and you calculate the stress from Hooke's law. So I will finish at this point this session. Next one, I will do an example for you by a simple. We'll start with a simple example. We will divide the domain in finite elements. Well, we'll make a mesh of not many elements, because I'm going to do end calculations. As you can see, if the number of elements is too high, it means we stay here all day doing these calculations, end calculations. So I will do maybe a one-dimensional problem first, and then we can maybe do a two-dimensional problem with maybe a maximum of 2 or eventually 4 elements. So I will design that example for the next session. And then I will show you all how to do this step by step. This is what is being done in the background in this finite element software, okay? So I hope you managed to follow this. See you in the next session. Take care. Bye-bye.